Hello Math 2, this is Mrs. Bricky and this video is for Unit 6, Lesson 5. We're going to be talking about tangent lines today. So just to go over a teeny bit of vocabulary before we start, a line that intersects the circle at 2 points is called a secant line. And every secant line has a chord, that's a chord. Just the portion of the secant line that's between the 2 points inside the circle is called a chord, and the secant is the entire line. If a line intersects a circle at exactly 1 point, that's called a tangent line. And the point that it intersects the circle at is called the point of tangency. So it just touches in that one spot. So on diagrams, tangent lines are often represented by just segments. Instead of seeing the whole line, you see just parts of just a segment of the line. And in some cases, it's easy to tell that something is tangent, and in other cases, it's a little bit trickier. So sometimes when we see both of the sides, we can tell straight away that that's a tangent. We can tell it's just touching the circle at just this one point and that that's a tangent. It can be harder to tell if it only touches the circle or if it only shows you half of it, like this one right here. That is a tangent segment. If we extended it a little farther, you could see that it's just touching at that one spot. But sometimes when that one spot is where it stops, it's a little bit harder to tell. But that is also a tangent segment. So I'm going to start highlighting the tangent segments in yellow. So this one is definitely tangent. The other one on this diagram definitely is intersecting the circle at 2 points, so that one is not tangent. The one I highlighted in green is tangent, as are these two. This one's tangent with a point of tangency right here, and this one is tangent with a point of tangency right here. So we actually have on this diagram 3 tangent lines. On the next one, there's actually only one tangent. Sometimes it's helpful if you think about extending one of the lines. So if I extended this, it's not doing what I wanted it to do. If I extend this line, you can see it would intersect the circle at 2 spots, and if I extend this one, you can see that it would touch at 2 spots, but if I extend this one, you can see that it doesn't. It just has that one spot. So this one over here is a tangent segment with a point of tangency right here, but the other two are not tangents. And again, sometimes extending it can help you see the 2 points that it would intersect the circle at. All right, our last diagram over at this side, we do have just one tangent. It's this one. The other one you can see would intersect the circle in 2 spots if we extended it. So this one would not be a tangent. And definitely the one inside is just a chord. All right, so now that we can see how to look for tangents, we have a couple of theorems about tangents. The first one says that tangent lines are perpendicular to the radius of a circle at the point of tangency. So if we've got a tangent line, it has that point of tangency right there. If we draw the radius to that point of tangency, that's going to create a 90-degree angle between the radius and the tangent line. So here's a couple of examples where we can use that fact. So on their first diagram, we have AC is tangent to circle B, and B is the center of the circle. So we know that this is a 90-degree angle, and our goal is to calculate the length of AB. So on the diagram, that would be this length right here. Well, that's a right triangle right there, so we can use the Pythagorean theorem. The legs have a length of 7 and 24, and I'm going to call this distance x just for the sake of my equation. So Pythagorean theorem says leg squared plus the other leg squared is equal to the hypotenuse squared. So 7 squared plus 24 squared, I need my calculator. 7 squared plus 24 squared is 625 is equal to x squared. And so now we can finish solving by taking the square root of both sides of our equation. We don't need the plus or minus symbol because we're looking for a length of a segment here, so we're going to have a positive answer only. And the square root of 625 is 25. So we have the length of AB is 25. Okay, over here we have a segment from S to T that is tangent. So here's our point of tangency. It's RS is a radius of the circle, so that tangent segment is perpendicular to the radius RS. So we have a 90-degree angle there. Now our goal here is to figure out x, and this x is only the distance from the edge of the circle to point T. So we're only looking for that little bit. But what we're going to do is use the Pythagorean theorem like we just did to calculate this whole length. And then we know that this part of it is also a radius, so that is length 5. So let's call this hypotenuse y. So leg squared plus other leg squared is equal to the hypotenuse squared. 5 squared plus 12 squared is 169. So when we square root that, we get 13. So y is equal to 13. We're looking for the length of x, so we know this whole segment is 13. Well, it's from R to the edge of the circle is the radius, that's 5. So from the edge of the circle to T has got to be 8. So 5 plus 8 is 13. So x is equal to 8. Okay, this example looks so similar to the other two, but it's actually a little bit harder to calculate. So we know that the distance from the edge of the circle to point A is 9. And what our question is that we're trying to answer is, what is the radius of the circle? So I'm going to call that R. And we have two radii in this diagram. And we know that AB is tangent, so we know we have a 90-degree angle right there. So we are going to use the Pythagorean theorem. The thing that makes this tricky is that we are going to have to use the hypotenuse here from A all the way to C, and we don't know how long that is. And we also don't know this other leg, so we're going to have to call the hypotenuse R plus 9. We don't know how long it is. We can't just call it a number. We can't give it a variable name by itself because this one also is just a variable R. So we have to just call it R plus 9. So when we do Pythagorean theorem, our A squared, let's see, our leg squared is R squared and 15 squared. And when we do our hypotenuse squared, it's going to be a binomial squared. It's going to be an R plus 9 that is squared. So on this side, we have R squared plus 225. But when it says R plus 9 squared, it means to take an R plus 9 and multiply it by another R plus 9. So that's R squared plus 9R plus another 9R and then plus 81. We have to fully multiply it. We can't just distribute powers. Powers don't distribute. We've got to multiply it. Now we can combine these two terms together. So we have the equation R squared plus 225 is equal to R squared plus 18R plus 81. And remember that 18 just came from combining the two 9Rs together. All right, so this looks like a pretty hard equation to solve, but something nice kind of happens. Right here, if I subtract R squared, they are gone from both sides of the equation. So I'm back to an equation that is not too tricky to finish solving. The really difficult part of this problem really comes right here when we square out that binomial. So we're going to finish up by subtracting 81. 225 minus 81 is 144. And now I just need to divide by 18. So that tells me that the radius of the circle is 8, and we have finished the problem. So this is a very tricky one. You do have to use a binomial for the hypotenuse to solve this. So it's a bit tricky. Example 3, we could also, if we had an angle, we could also use trig ratios to solve because we have right triangles here. So we'll just do these couple examples using trig. ST is tangent to circle R. That means this is a 90-degree angle. We're looking for the length of ST. Well, there's two ways you could figure out this length. You could set up a SOHCAHTOA equation, a sine, cosine, or tangent equation, or you might recognize that that's a 30-degree angle, so this is a special right triangle. If you recognize the special right triangle, you can go straight to the answer. If you don't, you might use a tangent. ADJ. So the tangent of 30 degrees is equal to the opposite over the adjacent. So if we solve for x, we'll multiply both sides by x and now divide by tangent 30. And if we do 7 divided by the tangent of 30 degrees, we get 7 root 3. So either way, we get that same answer. It's nice if you know your special right triangles to be able to do it a little quicker without, writing out a formal equation. But either way, you get the same answer. In this example, we can't use special right triangles because that's a 24-degree angle, so we'll have to do a little bit of trig. We're looking for the radius of the circle, so I'm going to call that x. We know that it's a tangent, so we know that's a 90-degree angle, so we can think of our labels from the 24-degree angle. The x that we're trying to find is the opposite, and the 16 is the adjacent. So we can do the tangent again. Tangent 24 equals x over 16. And we are almost there. We need to multiply both sides of our equation by 16. And I got 7.12 for x. Okay, here's a circle and a point that is on the exterior of the circle. How many lines through the point are tangent to the circle? Well, if I'm trying to connect a point to be tangent on the circle, it's going through this point, and you can see all the way through here, it's not tangent because it's intersecting the circle at 2 points, but there's definitely one right here on this side of the circle, but then there's another one on the other side. So there are 2 lines through the point that are tangent to the circle, one to each side of the circle. And it wouldn't be possible to draw any more than that. All right, so tangent segments from a common external point are congruent. So if I draw the tangent line from point A to each side of the circle, it's going to create these 2 congruent pieces. So here's a diagram. We want to decide which 2 segments are congruent and solve for x. So when dealing with tangents, you want to check and see if you have 2 tangents that are from the same point. So thinking about point C, I definitely have the one to this side, but I don't have the one to the other side. This is close, but that is not quite tangent. I would need this tangent. segment. So I can't use those two. Thinking about the other points that are exterior to the circle, I have point H, so I definitely have a tangent from this side, but from this side, I don't quite have another tangent. Definitely not tangent to point C. So I don't have a situation of two congruent segments here. So let's think about point A. Point A to point B is a tangent segment, and point A to point G is a tangent segment. So those are the two in the diagram that are equal to each other. So we can solve for x by setting those two equal to each other. 2x minus 3. So x plus 4 is equal to 2x minus 3. So to solve for x, I'm going to subtract x from both sides of the equation, and I'm going to add 3. So getting all my constants to the left and all my variables to the right, those ones cancel and those ones cancel. So we have 7 is equal to x. And that's our x value. So this segment right here has a length of 11, and this segment right here, 2 times 7 minus 3 is also 11. All right. Here's another diagram. We've got point A exterior to the circle, and it shows right angles here and here. Well, if a segment is at a right angle to the radius, that is a tangent segment. So we do have this segment is equal to this segment. So setting them equal algebraically, x squared is equal to 6x plus 16. This is a quadratic, so we're going to have to do some factoring. I'm going to subtract both of those so that I have all of the terms on one side of the equation equal to 0. Now we can try to factor it. It's been a while since we factored, so start with your leading term. That's going to put, we need an x leading each of our binomials so that when they multiply together, they create that x squared. Then shift your attention over to that ending number. We've got a negative 16. The factors of negative 16 are, we could have a plus and a minus. We could have 2 and 8. We could have 1 and 16. We could have 4 and 4. We're looking for a combination. I could switch all of those signs as well. We're looking for a combo that gives us negative 6. So that's our combo. X plus 2 and x minus 8. So we've got each factor gives us one of our answers. And remember, it's been a while, so formally we're thinking about what x value makes each of those factors equal to 0 to get our two answers. So we would subtract 2 to get our first solution, x is equal to negative 2. And we would add 8 to get our other solution, x is equal to 8. And really, both of those x values are fine. So I just want to show you that that works. Sometimes with diagrams and geometry type of things, we want to, say that the negative answer doesn't work. But in this case, the negative answer is fine. Here's a mini version of our diagram. If x equals negative 2, this is 6 times negative 2 plus 16. Well, that's actually 4. And this is negative 2 squared, which is 4. So if x is equal to negative 2, that just means each of those segments has a length of 4. If x is equal to 8, this bottom segment would be 8 squared, which is 64. And then this top segment would be 6 times 8 plus 16, and that is also 64. So we don't have enough information to know which of those two answers is correct. For this diagram, both of them are correct answers. If we had the size of the radius, that might tell us which one is true, but we don't know anything else about that circle. So both answers, negative 2 and 8, are true solutions to this equation. All right, x is equal to, oh my gosh, Wow. I've been making too many videos today. We have example 6 here, and we don't have any x's, so we don't know x is equal to nothing. All right, example 6. We've got a quadrilateral with a circle inscribed in it. We want to find the perimeter of this quadrilateral. And at first, when you see these, it seems almost impossible to solve them. But if you notice that we have 4 points outside of the circle, and each of the points is connecting tangentially to the circle. So this segment right here from C to that point of tangency is 5. And we have the tangent on the other side of the circle as well. So this segment is 5. And if you're thinking about point B up at the top of the circle, that's an external point and it connects to 2 points of tangency as well. So this segment has a length of 10, and this segment to this tangent point would also have a length of 10. And we have external point A right here, and it connects to this point of tangency right here with a length of 3. So the other side also has a length of 3. Down at the bottom, we have a segment 12. From D to C is 12, and we know from C to the circle's point of tangency is 5. That means this one has a length of 7, and from D to the other side tangent to the circle also is length 7. So we can kind of think through all of these little scenarios. Each of them, it's like having 4 of these on the same diagram, each of those connecting to the circle at 2 points of tangency. To get the perimeter, we just need to add all of those up, and you can add them up, however you see. Um, you can add them up individually, or you can look at the whole side lengths. We've got a couple of 10s, we've got a couple of 5s, we've got a couple of 7s, and a couple of 3s. And again, there's a lot of ways you could see to add these up, but we just need to add them all up however we see them. That is 50. So we've got a quadrilateral with a perimeter of 50. Our last theorem deals with the angle that is created by a tangent line and a chord. So I have this demo to help you see what we're talking about here. So right now I have an inscribed angle of 22 degrees. That means that I have an arc that has a measure of 44 degrees. I'm going to now move point D down the circle a little bit. So that's making that angle larger. So right now it's a 55-degree angle. Well, that means I have 110-degree arc. Remember, for an inscribed angle with its vertex on the edge of the circle, the arc measure, the intercepted arc is going to have twice the measure of the inscribed angle, so double it. So if I move D and make that angle even bigger, it's now 62, 64, 66, 70. When I get right there to point D, so that that angle is 74 degrees. And so the arc, like I lost my tangent line completely. My arc is going to be twice that. So even at the extreme case where I bring that secant line down until it's actually just a tangent line, it's going to still be double that inscribed angle. So if the angle right there between the tangent and the chord is 74 degrees, which I can't get it to land on, but that's exactly 74 degrees, then the arc would be 74 times 2, 148. So here's our theorem. If an angle has its vertex on the circle, then the angle measure is 1/2. That's so funny. 1/2 the measure of the intercepted arc. So this works for 2 chords, like you can see in my first diagram, and it works for a chord and a tangent line as well. So whatever that angle is between either between the two chords or between the chord and the tangent line, the intercepted arc is going to be 1/2 of that measure. All right, so we've got a couple diagrams here. So first of all, we have an arc measure that is 146 degrees, and we would like to find this angle measure. Well, that angle is just going to be 1/2 of the arc, so that would be a 73-degree angle. In our second diagram, so when the angle shows up on the interior of the circle like that, it's talking about this angle right here is 116, and we are trying to calculate the length of the arc from J to L to K, so this major arc. Well, to get the arc from that angle that has its vertex on the edge of the circle, we just double it, so that is a 232-degree arc. And the last one, the measure of angle MPQ is our goal. So this one is one that we have to figure out sort of indirectly through a couple of steps, but our goal is to get this angle right here between that chord and that tangent line. So we've got a 160-degree arc right here. Well, there's kind of two paths you could take here. Let's use that arc. So this arc is on one side of that secant line. That means that this arc that I'm going to draw in blue has to be 360 minus the red arc. So this is a 200-degree arc. And that means that this angle that I have marked in pink has to be 1/2 of that. So this is a 100-degree angle. So the measure of angle MPQ is 100 degrees. We could have also found that by figuring out this angle is 80, and those two together have to add up to 180. All right, that's it for this lesson. Let me or your teacher know if you have any questions. That's it for the circle unit. So unit test review coming up soon. So if you're a little behind or you have some questions that you haven't been able to get resolved yet, make sure you get those resolved as soon as possible. Thank you.